Good morning, everyone. My name is Ramya, and my advisor is Professor Grace Cow. I'm a PhD student at University of Illinois Urbana-Champaign and a visiting student at Stanford. Today, the topic of my presentation is on GPS spoofing mitigation and timing risk analysis in network PMUs via stochastic reachability. To perform wide area stability monitoring, power grids utilize advanced devices known as phasor measurement units, in short PMUs. The figure on the right shows a map of more than 2,500 PMUs that were deployed across the US by the year 2017 and the associated communication links connecting them. Each PMU is equipped with a GPS receiver to precisely timestamp the voltage and current phasor values. A network of geographically distributed GPS receivers facilitate time authentication by cross-checking among each other and thereby eliminate the need for a reference receiver. Networked approach in power systems overlay the existing PMU infrastructure and therefore can be implemented without any additional hardware. However, GPS civil signals are susceptible to spoofing because of unencrypted signal structure and low power. According to IEEE C37118 standards, to ensure grid stability, it is essential that the timing error at any PMU should not exceed 26.5 microseconds. Therefore, secure GPS timing is of paramount importance for reliable PMU operations. The key measures of secure GPS timing are spoofing attack mitigation and timing risk analysis. Here we define risk as the probability of estimation error to exceed a safety alert limit. As seen in the equation on this slide, we set the safety alert limit to 26.5 microseconds to ensure that the timing errors comply with the IEEE standards. The state-of-the-art methods on networked anti-spoofing mostly fall under point-valued state estimation techniques. Some examples include use of encryption codes, angle of arrival and time difference of arrival analyses, attack magnitude estimation, and so on. However, the limitations of these approaches are that they do not account for the stochastic bias in measurements that cause the point-valued state estimate to drift over time. Also, no safety guarantees are provided on the estimated GPS timing and attack mitigation. Furthermore, these methods are applicable only for certain spoofing types and are not universal to all. Given these shortcomings, the objectives of this work are to compute secure GPS timing across a network of receivers, mitigate spoofing attacks such as weakening, signal level spoofing, coordinated attacks, and so on. Quantify the probability of estimated GPS time to violate the IEEE C37118 standards. Based on the objectives, the outline of this presentation is shown in the slide. I will first explain our proposed algorithm on stochastic reachability based distributed Kalman filter, in short known as SRDKF, and its various modules. Next, I will describe our simulated experiment setup of coordinated signal level spoofing and later validate the improved state estimation accuracy of our SRDKF and its robust timing risk analysis. In the end, I will summarize my talk. Our algorithm on stochastic reachability based distributed Kalman filter is based on three main aspects. First, we utilize a network of GPS receivers geographically dispersed across the US. In addition, we leverage the stationary infrastructure of power substations to obtain the known receiver positions, which are used to aid our algorithm. Our next important aspect is to perform distributed processing in an asynchronous manner. This is important because GPS time is manipulated during spoofing and therefore there is no reference time source to schedule the conventional send-receive requests within the network. The third aspect is to perform state estimation using the concept of stochastic reachability. In particular, we developed a distributed Kalman filter framework in the set value domain instead of point valued. In our SRDKF, we consider the global states to be the GPS time and its drift rate, wherein each receiver in the network computes a local estimate of this 2D global state vector. Following up on our design aspects, in this work, we develop a set-valued framework of distributed Kalman filter to perform secure network time authentication. The figure on the left illustrates our set-valued approach. As compared to point-valued, set-valued approach has many advantages. It computes not only the point-valued mean of states, but also their set-valued bounds, and thereby provide the probability of violating the safety alert limit. Set-valued approach does not require any assumptions on the distribution of states or measurements. They only need the error bounds on system dynamics and measurements in non-spoofed conditions. Our current work is inspired by a set-valued formulation designed for stochastic processes known as stochastic reachability. Stochastic reachability is widely used in robotics for path planning, but no prior work exists on their application in the field of power systems. Stochastic reachability computes a set of stochastic reachable states given an initial set and known error bounds. In this context, we parameterize the stochastic reachable set using a set representation known as probabilistic zonotope, in short P-zonotope. An example of a 1D P-zonotope is shown in the slide. In particular, a P-zonotope is an enclosed probabilistic hull that collectively captures the non-Gaussian and time-varying nature of stochastic measurement errors. Mathematically, the P-zonotope is characterized by three parameters which are also pointed out in the figure. The center is indicated in red, the width of the hull in green, and the tail or covariance of the P-zonotope is indicated in blue. The key contributions of this work on SRDKF are that we develop a set value DKF to propagate probabilistic zonotope of state using stochastic reachability. We design a two-tier approach. First, we perform spoofing mitigation at measurement level by analyzing the deviation of received measurements from their expected stochastic set. Secondly, we quantify the timing error at state level by calculating the intersection probability of the estimated P-zonotope of state with the unsafe set, which is defined based on the IEEE C37-118 standards. This figure shows the architecture of the proposed SRDKF that is executed independently at each ith receiver. It comprises of four main modules: time update, spoofing attack mitigation, measurement update, and timing risk analysis. Analogous to the conventional point value DKF, we perform set value time update to compute the predicted P-zonotope of global state vector. Thereafter, we utilize the predicted P-zonotope and the received GPS measurements to adaptively estimate the attack status. Next, the GPS measurements and the estimated attack status are broadcast and received across receivers within the network. In measurement update, the GPS measurements and their attack status from neighbors are collectively processed to compute the corrected P-zonotope. Now, the center of this corrected P-zonotope provides the estimated GPS time, while the bounds are further analyzed to compute the timing risk. Thereafter, the process repeats for the next time iteration. Now, let's look at each of these blocks in more detail. Analogous to the conventional point value DKF, the set value DKF also has two main steps. One is time update and the other is measurement update. In time update, we compute the predicted P-zonotope of global state vector from the corrected P-zonotope of previous time and process noise bounds. We perform offline empirical analysis to estimate the error bounds on the system dynamics and communication latencies. An example of the 2D predicted P-zonotope is shown in the figure on the left. The right figure shows a 1D P-zonotope of time bias that corresponds to the 2D P-zonotope, which is sliced along the time drift axis. We perform set addition of process noise bounds indicated by orange and corrected p-sonotope indicated in gray to compute the predicted p-sonotope. Our next step is spoofing attack mitigation. At each receiver, we independently analyze the GPS measurements to compute its attack status. For this, we obtain the measurement error bounds in non-spoofed conditions from the offline empirical analysis of OpenSky GPS data. Next, we compute the expected p-sonotope of measurement residual from predicted p-sonotope and known measurement error bounds. The expected p-sonotope, as illustrated in the figure, is indicative of the stochastic errors in the measurement residuals during non-spoofed conditions. The attack status quantifies the deviation in the measurements from the expected p-sonotope and lies between 0 to 1, with 0 being most likely authentic and 1 indicating that it is spoofed. Next, we perform asynchronous data transfer within the network, wherein each receiver shares their GPS measurements and estimated attack status with their neighbors. After this, similar to time update, in measurement update, we perform set addition to compute corrected p-sonotope from predicted p-sonotope and measurement error bounds of its neighbors. The adaptive Kalman gain associated with the measurements of each jade neighbor is proportional to 1 minus their estimated attack status. The center of this corrected p-sonotope is the estimated GPS time, which is later given to the PMUs, and the width and covariance are further analyzed to estimate the associated timing risk of the estimated GPS time. To perform timing risk analysis, we first define the unsafe set with timing error greater than plus or minus 26.5 microseconds. This is indicated by the gray stripes in both the figures. Next, we over-approximate the corrected p-sonotope by finite polytopes. An example of over-approximation of p-sonotope by 4 polytopes D1 to D4 is shown in the figure on the left. Thereafter, we compute the area of intersection of each of these polytopes with the unsafe set. The figure on the right shows the top view of this over-approximated series of polytopes. An example intersection region of D3 polytope with unsafe set is indicated by red cross marks. The timing risk is defined as the sum of cross polytopes of their intersection area with the unsafe set times the maximum probability. As labeled in the figure on the left, the maximum probability is the value of probability indicated by the top face of each polytope. We also add a constant bias to account for the tail of the p-sonotope that is not captured by the polytopes. Now I'll talk about our simulated experimental results that validate the performance of our SRDKF algorithm. We consider a network of 7 GPS receivers sparsely connected as seen in the figure on the right. Considering a simulated experiment duration of 1500 seconds, we induced a simulated attack of coordinated signal level spoofing, where receiver 5 experiences a time walk of 100 nanoseconds per second for 1000 seconds, and receiver 1 experiences a time walk of 400 nanoseconds per second for 600 seconds. We generated GPS measurements using an open source GPS simulator, and we utilized MATLAB Continuous Reachability Analyzer, aka CORA toolbox, to implement stochastic reachability framework. In the first set of experiments, we demonstrate the improved state estimation accuracy across a network of receivers using our SRDKF algorithm as compared to the conventional point value DKF. The maximum state estimation error in the network using the conventional point value DKF is 74.5 microseconds in time bias and 125.3 nanoseconds per second in time drift. We observe from the figure on the right that both receiver 1 and 5 violate the IEEE standards, which are indicated by the dashed magenta line. However, the maximum state estimation error due to our SRDKF is only 8.4 microseconds in bias and 33.2 nanosecond per second in drift. Therefore, the GPS time estimated by our SRDKF at all the receivers in the network comply with the IEEE standards. In this slide, we show the intermediate results of our SRDKF algorithm. That is, we show the attack status of 4 among the 7 GPS receivers in the network. Here, an attack status of 0 indicates that the measurements are authentic, whereas 1 indicates most likely spoofed. We observe that our SRDKF adaptively mitigates spoofing in receivers 1 and 5 and successfully estimates other receivers to be non-spoofed. Now, let's analyze the estimated GPS timing risk. In this slide, we plot the timing risk of 4 out of the 7 sparsely connected GPS receivers. The communication network is shown on the right side, where green tick indicates the presence of communication and red cross indicates otherwise. We observe a strong correlation between the number of non-spoofed receivers available for crosscheck and the timing risk estimated. At receiver 4, when none of the 4 neighbors are spoofed, the risk magnitude is low and in the order of 10 power minus 7. In contrast, at receiver 3, where 2 out of 3 receivers are spoofed, high timing risk of 0.3 is observed. Similarly, when 1 out of the 3 neighbors at receiver 1 is spoofed, the order of timing risk magnitude is 10 power minus 3. And when 1 out of 2 neighbors are spoofed at receiver 5, the risk is a higher value of 0.1. Therefore, our SRDKF successfully quantifies the risk of violating the IEEE C37-118 standards across all receivers in the network. In the next set of experiments, we perform sensitivity analysis of risk as the number of crosscheck receivers are increased, in this case from 2 to 7. We also tested for 4 different magnitudes of weakening attack, that is 30, 45, 60, and 100 microseconds. For each case, we performed 15 Monte Carlo runs. We observed that as the number of crosscheck receivers increases, the risk associated with timing decreases. Also, irrespective of weakening magnitude, when the number of crosscheck receivers are greater than 5, the variation in risk is less than 10 power minus 5. Therefore, our SRDKF only requires a handful of receivers to estimate a robust measure of timing risk. To summarize, in this work, we developed an SRDKF framework to compute secure GPS time for a network of receivers that performs spoofing mitigation at measurement level by analyzing the deviation of received measurements from its expected set. And we also analyze the timing risk at state level by using the intersection of estimated p-zonoto with unsafe set, where the unsafe set is a set that violates the IEEE C37-118 standards. During a simulated case of coordinated spoofing, our SRDKF demonstrated successful mitigation of spoofing and improved state accuracy, and also performed robust risk quantification for all the receivers in the network. We want to thank the Department of Energy for funding this project, and also special thanks to all the members of NAVLab for the insightful discussions. Thank you, and I'll be happy to answer any questions.